Section 15.6, triple integrals, which happens to be generalization of the double integrals. Recall in functions, evaluating the definite integrals for a function of single variable, we had to divide the number line into subintervals. For double integral, we had to divide the closed region, whether it's rectangular or general, into subrectangles. In this section, we have triple integral, which is performed over a solid. Remember, single variable functions are performed over a closed interval. Double integrals are performed over a closed region. Triple integrals are performed over a bounded continuous solid. So instead of dA, now we have a volume element, dV. In this case, dV can be dx, dy, dz, or any 5 other combinations, because there are like 6 other ways you can permute dx, dy, dz. So there are a total of 6 ways. Remember, in double integral, we can switch the order in 2 ways, either dx, dy, or dy, dx. But for triple integrals, we can switch these 3 elements of y and x and z in 6 ways, because that would be like 3 factorial, which is 6. Here you have 2 factorial, which is 2 ways. So the formal definition of triple integral is limit of what? Triple Riemann sum as m and n and l approach to infinity. So this is how it looks like. So the summations, what gets to be multiplied by volume element. So the triple integrals always exist if what? F is continuous, and this sample point is somewhere in our sub boxes. So what happens is we're going to divide the three-dimensional space into what? Into sub boxes. And we're going to take one of those typical box. Notice the length and the width of the height of the box is dy, dx, dz. So the volume element is dx, dy, dz, which is length times width times height. For the first case of triple integrals, you may have a rectangular box. In other words, x might go from constants a to b, y might go from c to d, z might go from r to s. So what you have to do is divide a to b into l many subintervals, and dy cd into m many, so that's your delta y. This guy was your delta x, of course, with equal width. And the interval from, let's say, r to s into n as an n, c many subinterval, and that would be your delta z. So that's basically where l and m and n come from. So if you perform the summation and let the number of subintervals in each direction approach to infinity, lo and behold, that would be the definition of the triple integral, which is performed over a solid, and this guy is a volume element. So now, in order to evaluate this triple integral, you always start from the innermost integral. Just suppose dv, in this case, happens to be dz, dy, dx. So what you have to do, and imagine we are on a closed rectangular box. In other words, x goes from -1 to 1, y goes from 0 to 2, z goes from 0 to 1. So this is called a rectangular box. So what does that translate into is all the limits will be constant. So how do you do this? Well, as I said, you start from the innermost integral. So notice first you evaluate or integrate this function with respect to x. So what you do, you keep x's and y's constant. So what you get is what? X z squared over 2 minus what? A y cubed times z. But z goes from 0 to 1, so evaluate this. And then you would get this. Next, you would perform the integration with respect to y. So what you do, you keep what? X is constant. And now this would be like what? X over 2y minus y to the 4 over 4, but y goes from 0 to 2. Evaluate this. Now you are back to what? A single variable function, x minus 4. Evaluate that or integrate that and evaluate it between -1 and 1. And lo and behold, you get -5. Remember I mentioned that when it comes to triple integral, there are 6 different ways you can change the order of integration. Remember, you can go dz, dx, dy, dx, dy, dz, dx, dz, dy, dy, dx, dz, and dy, what? Dz, dx, and let's see now, and right here I could have gone, let's say, dz, dy, dx. So that would be like 6 different ways of evaluating. So you may switch the order of integration, provided what? The limits, just like double integral, happens to be constant. However, in this case, you are not on a rectangle, you are on a rectangular box. So this is a rectangular box. So what is the meaning of you are on a rectangular box? That means the limits of all 3 triple integrals, they have a constant limit. Remember, Mr. Fubini proved that what? If the limits are constant, so the order of integration doesn't matter, but be careful, there are occasions that they may not come up the same, even though the limits may be constant, so you got to always make sure the integrand is continuous and bounded. So in previous problem, I did this, I came up with -8, right? But notice the order of integration was dz, dy, dx. So here I went dy, dx, dz. I just switched the limit. So according to Mr. Fubini, I should come up with the same answer. However, the catch is, if the triple integral performed over a general solid, you know, not rectangular box, not a rectangular box, then the order very much matters. And the way we do this is as follows. When you set up a triple integral over a general solid, the first one goes from surface to surface. That would be the limits of the first integral, the innermost integral. The second one goes from curve to curve, and the last one goes from point to point. In other words, regardless of whether you have rectangular box or not, the last integral, the outer integral, is always constant. It's never variable. Do you see it? So once again, this would be like from surface to surface, curve to curve, point to point. As a matter of fact, here you are in 3 dimension, but when it comes to the limits of the what? The last 2 limits, as you go from right to left, you are on the x and y axis. So now the question is, evaluate this integral, which is y dv. Notice they didn't tell you what dv stands, what the order of dv should be, so it's entirely up to you to choose one of those 6 ways of setting this triple integral. The question is, evaluate this if E is the solid bounded by these planes, so those are the coordinate axes, and the plane, what? 2x plus 2y plus c is equal to what? 4. Turns out, if you, what? Kind of graph this, okay, in what? First octant, all right? So the resulting solid will be 4-sided pyramid. Notice 1, 2, 3 in the front. And that's called tetrahedron. All right. So now this would be your region R if you what? shine a light from the top and see the projection of this on the floor, which happens to be this triangle, and it hits the what? X and Y axis at what? 2, 2. Excuse me. Suppose I went with this notation or this setup, dz, dy, dx. So z goes from surface, the bottom surface, so that would be z is equal to 0, which happens to be the floor, till it goes and hits the what? Four-sided pyramid, which is z is equal to, solve this guy for z, which is 4 minus 2x minus 2y there. However, when it comes to the limits of the last two, as you go from right to left, you got to draw this region on the x and y plane. Now, depending how you take your rectangular element, so in this case, I'm taking it vertically, so that's why I'm going dy dx. Had I taken the elements, what, horizontally, then this would indicate that I have to go dx dy, whereas here I'm going dy dx. So once again, if you take your element vertically is dy dx. If you take it horizontally is dx dy. Same idea applies to if you were on the yz axis or xz axis. Alrighty, so let's see now. So the limits would be what? 0 to the pyramid. But when it comes to y goes from the x-axis, so this is x-axis, which is a curve, to this curve. And the equation of that curve is what? X plus y is equal to what? 2. Solve for y, so you get what? Y is equal to negative x plus 2, and as you can tell, x goes from 0 to 2. Notice the last outer integral, rain or shine, regardless of what kind of integral you do, whether it's double or triple, is always constant, always. So notice this is what? This is a plane, so that's the surface. This is the floor, that's the surface. But notice this is a curve, which is the what? Which is the x-axis. This is a curve, which is what? The line. And these are like point to point. Do you see it? Point to point. So the setup of triple integral could be tricky, but it takes a little bit of practice so you can get used to it. All right, next one is evaluate this. Notice they didn't tell you which order to take, but E, you know, this solid, is bounded by what? These cylindrical surfaces. So these are called cylindrical surfaces. And the planes, z is equal to 1 and z is equal to what? X plus y. Immediately what? Graph your region on the x and y axis. Notice y is equal to x squared is this parabola, and x is equal to y squared is that parabola, and I believe they intersect each other at what? 1, 1, 0, 0, and 1, 1. So then again, remember, because you're going z, so what? This has to be, I mean, it didn't matter if you would have gone like x or y, this would be still what? Surface to surface. Okay, surface to surface, correct? In this case, the surfaces are what? Floor and the plane. This guy is a plane. But when it comes to what? Writing the limits of the last two integrals as you go from right to left, now you got to refer to your diagram and see what kind of rectangular element are you taking. If you take horizontally, that would be dx dy. If you take vertically, that will be dy dx. But notice you're going from the bottom curve, which is x squared, to the top curve, which is what? Square root of x. So you have to solve this for y, so you get the square root of x. In other words, we're going from bottom to top. And when it comes to x, we're going from left to right, which is what? 0 to 1. Once again, notice the outer limits, rain or shine, will be always constant. Special case, if the integrand, this guy right here, happens to be identically equal to 1, then the triple integral is finding the volume of the solid itself. So that's a special case. Keep that in mind, please. Finally, let me just make a quick comment about this. Remember I said there are 6 ways you can what? Set up the order of triple integrals. Let's say you're trying to evaluate this, even though I don't know what the integrand is. That's not the issue. The issue is how would you permute these? You know, here it is. Can you write it as an equivalent integral in 5 other ways? Believe it or not, if you would graph these, this solid, notice z goes from 0 to y minus 1, y goes from the square root of x to 1, x goes from 0 to 1. Believe it or not, if this is your solid E, and this is how the graph of solid E looks like. Now, if you shine a light from the top, you will see this. And that you will see this right here, right there. And that guy is right there. So z goes from 0 to what? This plane, y minus 1. But then again, it all depends whether I take my element vertically or horizontally. If I take it vertically, that's dy dx. If I take it horizontally, that's dx dy. And yes, it matters, when it comes to the limits. Because if you go dy dx, you're going from square root of x to y equals 1. You remember, this is like curve to curve, and x goes from 0 to 1. However, if you go dx dy, you take in your element horizontally, you're going from what? The y-axis, which is x is equal to 0, to this guy, which is x is equal to what? Y squared. And then again, y goes from 0 to 1. So that's 2 ways. On the other hand, if you shine a light, via x-axis, so this is how the graph looks like, this is how the projection of the solid looks like on YZ plane. So this guy was XY plane projection. This is YZ plane projection, which is just it's just this triangle. Then again, now you have dx dy dz and dx dz dy. And this is how the region looks like. Once again, notice x goes from 0 to y squared, correct? X goes from 0 to y squared. But now, y and z, you get it off of here. So if you take the let's say horizontal element, like so, you're going from where? You're going from the y-axis to this line. So that would be z is equal to, let's say, y minus 1, and y goes from 0 to 1. Once again, the outer limits, they're always constant. On the other hand, if you take the element vertically, now that would be x goes from 0 to what? Y minus z, z goes from, y goes from 0 to 1. So we switch the the z and the y limits. Do you see it? So here it used to be these are the limits for y. These are the limit for these are the limits for y. Excuse me, guys. These are the limits for y. These are the limits for z. Sorry about that. But now, if you switch it, so these would be the limits of z, correct? And these would be the limits of y. Finally, what if I shine the light this way, from the right side of the solid? What am I going to see? I'm going to see this. So this would be like XZ plane. So this would be the projection on XZ plane. Then again, Y goes first, but then you have to permute X and Z. If you go dx dz, those will be the limits. If you go dz dx, those will be the limits. Notice it very much matters which way you set up the integral. The order matters, and it also matters what kind of projection are you looking at? Are you looking at this solid via what z-axis? Are you shining the light from the above or from the front or from the right side? Because depending how you shine the light, you get different kind of projections. Do you see it? These are the projections. Do you see it? Okay. And when it comes to the last two variables, then you can permute this. So you get two um, cases here, two cases here, two cases there. So that's a total of what? 6 cases. I know it's not easy, but it's not impossible. I just want to make sure that you all see that there are 6 ways, but what? To set up a triple integral. And at the end of the day, all these 6 setups should give us the same answer. Thank you.